Okay, let's continue and greet Oana Barbu, and she's going to talk about leveling up the T Attestation game on chain. Round of applause, please. Thank you.
Hi everyone, I'm Oana and, from Automata, and I'm going to tell you how we can make the attestation costs cheaper on chain. But before I talk about the attestation, I would like to ensure that we all have the same understanding of what TE is. A TE, or Trusted Execution Environment, is a memory enclave within hardware that prevents unauthorized access to the data and code stored inside it. Neither the operating system kernel nor the hypervisor can tamper with the enclave's memory. This is achieved by having the CPU encrypt the enclave's memory to protect its privacy and provide computational integrity. And it also ensures that only the enclave is able to decrypt its memory. Common implementations of TEs are Intel SGX and Intel TDX, AMD SEV, and AWS Nitro Enclave. We believe that TEs are very suitable for blockchain applications. Chances are that if you think about privacy and security for blockchains, you are most likely to think about zero-knowledge, fully homomorphic encryption, or multi-party computation. However, despite notable progresses in these technologies, they often come with high latencies, complex implementations, and computational overheads, and some applications may not be able to tolerate this. On the other hand, TEs do not rely solely on the elegance of math, but they are faster, cheaper, and more practical. And these characteristics make them very attractive for applications today. TEs, we can use TEs to implement roughly all we can implement in a standard computing environment, and we do so with minimal overheads that usually come from encrypting and decrypting the enclave's memory. At Automata, we leverage TEs to build coprocessors, TE coprocessors. For instance, we build TE coprovers for rollups. Coprover enhances the security of a rollup by independently computing the state transition and ensuring that the state transition that the rollup is proposing is correct. Therefore, if both the TE coprover and the rollup agree on what the state transition is, then we can have more confidence that the state transition was computed correctly. However, a fundamental challenge when we deal with TE coprovers or TE coprocessors in general is how can we ensure that the application we interact with is indeed running inside the TE. It is essential that we ensure the legitimacy of a TE before interacting with it to be able to accept the result it produced, or maybe sharing sensitive information with it. So if we imagine a scenario where two machines claim to be TEs, how can I verify that the integrity of the TE before engaging with it? And luckily, we don't have to blindly trust. We can actually verify that the TE is authentic. And this is done using remote attestation. Remote attestation is a security mechanism that enables a TE to prove its identity, integrity, and configuration to another party. By engaging in remote attestation, any external party can verify the authenticity of the TE and ensure it is running trusted software and configuration. During remote attestation, the TE produces an attestation document containing details about its identity and configuration, and this document can be examined by the verifier to check that the TE is following the established security policies and requirements. Only a legitimate TE is able to generate a valid attestation document, and thus any malicious effort to impersonate a TE will be detected. So let's take a look at what the attestation document contains to understand why that is the case. So the structure of the TE document might differ depending on what TE technology is being used, but all documents will have these three elements. So the first element is the enclave's identity, or the public key. This public key is linked to the TE manufacturer, and its private counterpart is inside the hardware, and only the enclave itself can access it. Besides this, we also have the enclave measurements. These are details about the enclave state, including the software that the enclave is running, its configuration, firmware, and others. And lastly, we have a digital signature that's produced using the TE's private key, and this ensures that the enclave identity and measurements are authentic. The next natural question is how do we know that the public key of the TE is legitimate and recognized by the TE manufacturer? I'm going to use Intel in this example, but a similar process applies to the other TE technologies as well. So we do this, we ensure that the TE is legitimate by having a chain of trust linking the TE public key to its manufacturer. In this case, the chain of trust is an X509 certificate. I'm not going to details of what this X509 standard is, but it's basically the same technology that allows you to verify that a website is authentic when you land on it. And the X509 certificate used by Intel uses the SCP-256R1 algorithm for digital signatures. So if, let's say, we want to verify the attestation document on chain, part of this verification will be to verify all the SCP-256R1 signatures that are part of the X509 certificate. And unfortunately, the EVM does not support SCP-256R1 natively, and this operation is quite expensive to do on chain. More precisely, a naive verification of an Intel attestation documents cost about 3 million gas to do on chain, out of which half of is spent on verifying SCP-256R1 signatures. And considering how much this operation costs, it seemed like a good idea to try and optimize it. So we tried to answer the question, how can we make SCP-256R1 verification cheaper? We thought about using precompiles. Incidentally, SCP-256R1 is a popular curve, and the precompiles for it are being adopted, at least on L2s. But there are other cryptographic primitives that are used in TE attestation, which are not as widely adopted. For example, AWS Nitro Enclaves uses elliptic P384 and SHA-384 for its attestation document, and we don't know if and when these precompiles are going to be widely available. So we also considered using rollups, but a significant drawback of optimistic rollups is that they use fraud proofs, and fraud proofs have a finality time of up to 7 days. And this is a very long time for waiting on a TE attestation. As I mentioned before, one of the benefits of using TE is their speed, and having to wait 7 days to establish whether a TE is legitimate is a very long time. And the ZK rollups also come with their own limitations. Validity proofs are notoriously difficult and time-consuming to compute, and they largely limit the functionality of ZK rollups to simple transactions like transfers and trades. However, zero knowledge is particularly useful for compressing computation, so we decided to look closer at using zero knowledge to reduce the computation required to do on-chain to validate the signature. So instead of trying to verify the signature on-chain, we wanted to offload this computation off-chain and create a ZK proof that shows the signature has been properly verified. This proof is succinct and efficient, and typically ZK proofs are fast to verify, but the question was, can we build a ZK proof that is cheap enough to verify on-chain? So we tried a couple of approaches. This is a summary. We started with a baseline of 330K gas per signature verification. This was achieved using Dymo's P256 verifier contract. And we shaved a third of the computation cost by using a basic ZK circuit. And we were able to further reduce this cost by using aggregation. And with aggregation, we were able to get to 120K gas per signature verification. So roughly what ZK Basic does is we have a ZK circuit, we feed the SCP-256R1 signature into it to produce a proof, and then we verify this proof on-chain. And with aggregation, we have this aggregation circuit that takes in multiple SCP-256R1 proofs and generates a aggregated proof that we later verify on-chain. Proof aggregation is a method that basically allows several proofs to be combined together and produce a new proof that proves all the validity of all the initial proofs. So in our case, verifying the aggregated proof costed about 480K gas, meaning that one signature verification was about 120K, which is a third of the initial cost. But then we thought, what if we can offload the whole attestation verification to a ZK circuit? Building a circuit capable of proving the whole attestation document is a very challenging task, so we did not do it ourselves. Instead, we decided to use a ZK VM for the task. ZK VMs are specialized virtual machines designed to ensure computations are performed correctly. And they are also capable of handling general computation. So therefore, all we had to do was write a Rust program that verifies the attestation document and let RISC-0 VM generate the proof for us. And to our surprise, verifying this proof on-chain only costed about 330K gas. So what this all means, by using ZK VMs, we were able to make the attestation verification 10 times cheaper, meaning that it's that much cheaper to verify that we are talking to a TE. Attestation is extremely important for TE-enabled applications, so this is quite a good result. But beyond this, I also want to share two more general lessons. The first one is that abstraction is a very powerful thing. ZK VMs are general and perhaps not as optimized as dedicated circuits could be, but they're more optimized than what most people can design. The ZK VM logic is written by experts in the field that know the inside out of ZK, and it turns out that these universal circuits are more efficient than dedicated circuits written by laymen. To put things in perspective, as I said, for our aggregation circuit, we were able to verify the proof using 480K gas, and that was just for the signature verification. Whereas with the ZK VM circuit, we were able to do everything in 330K gas. And moreover, ZK VMs remove the need to learn complicated mathematics and cryptography that are required to design ZK circuits. And the second lesson is related to the importance of using the right tool to achieve good performance and efficiency. At Automata, we are generally in the TE camp, and our co-prover showcases how TEs can help ZK applications. But this time around, it was ZK that helped TEs. And generally, we think that while ZK and TEs are seen as competing technologies, we believe that they are both useful tools to have in your toolbox. If you want to learn more about Automata, these are our socials. You can there you can learn more about our multi-prover AVS, our T block builder, and other projects. Thank you for your time, and I think I have some time for questions.
Thank you very much. Yes, if there are any questions, please. We still have some time. Looks like everyone is tired today, so thank you very much. A round of applause, and at 6:30. Oh, there is a question. Great.
Hello. I just have a simple question. Is any of these decentralized, or is like Automata running all the hardware for these services? How does it work? Is it a decentralized protocol?
So I'm not sure I understand the question. Can you repeat?
If it's decentralized, the Automata protocol, like, does it take requests for doing this trusted TE stuff?
Yeah, so you have a contract that will verify the attestation document, and that contract is deployed on chain.
But who's doing this? Is just Automata the company, or are there other participants in the? Is it like a network where anyone can participate? How does it work?
I mean, we just implement the algorithm for verifying the attestation on chain. But yeah, once it's on chain, it's decentralized.
Okay, understood. Thank you.
Hi. I just saw that you've been having a token since 2021, and I guess I wanted to understand a bit more how the token interacts, and how does the token, accrue economic value or transmit economic value in your ecosystem?
Currently, we don't use the product that we have with our token. So this is currently deployed on Arbitrum, on Cephalonia, on the testnet. So we don't deploy this on our...
This particular TE that you've been...
Yeah, this. And
then the token accrues value from other things that Automata has done in the past, or how does that work? How does the economic kind of incentivization work?
To be honest, I'm not the most capable person of answering that question. But yeah, I think it's the products that we try to build maybe help us gain more popularity.
Okay, thank you.
And one more.
Hello, thank you for the talk. So, if the hardware manufacturers, if they allow for signature schemes that are compatible with blockchains, like ED 25519, will there any need to have ZK verification on chain? We could just directly verify the digital signature schemes, right?
Yeah, so you can do it directly on chain, but because it's not supported, you basically spend a lot of gas trying to compute the verification.
Right. But if it comes to be possible, then we don't need this, right? I mean, I guess for aggregation, ZK is still useful.
Oh yeah, absolutely. Like if let's say SCP-256R1 is being adopted in the
Right.
in the EVM, then you don't need to do that. You don't need to do the offload of the computation anymore.
Right, right. But I think aggregation still makes a lot of sense, actually. Yeah, thank you.
Yeah. Actually, you like once instead of verifying a single attestation at a time, you can also verify multiple attestations in the future. Let's say by aggregating them. Yeah.
And actually, so you mentioned that you have used how was it? RISC-0 or
Yeah.
Right. Have you tried with other more like specialized circuits for like other more performant proving systems, or just RISC-0?
We try to use SP1 as well, but
Okay.
we are still working on that.
Ah, okay, cool. Yeah, thanks.
Thank you. Very good.